Alright, so in this problem, it's very much like the previous problem, but there is a change in physics, and I think people got a little confused by this. Um, this is a person pushing a lawnmower. So let's be clear. Um, that means the pushing force goes downwards like this. And another rule that we have for free body diagrams is that the forces always come out of the object. So we're going to have the weight here. We're going to have the normal force pointing up like this. We will have a friction force opposing the motion. And we're going to do the same thing that we did before, where we have a diagonal force here that I'll call the applied force. And let's just be careful in our labels. So we're going to have horizontally, we're going to have an FA in the x direction. And we're going to have an FA in the y direction. And once again, I really liked what people did when they said, all right, FA is 200 newtons happening at an angle of 35 degrees. And so they just went ahead and they calculated FAX and FAY using the same vector component math that we did last semester when I had you do those problems on your practice tests and real tests. So in this case, we can simply take the 200 newtons and multiply that by the cosine of 35 degrees to get a horizontal component of 164 newtons when we round. And similarly, we can take the sine component and that'll give us a vertical component of, when I round it, 138 newtons. And so these are the components I actually use in solving problems. So for example, when I want to get the normal force on the lawnmower, for every single question, whenever we ask for the normal force, what we want to do is we want to be clear that what we want to balance are the vertical components of the force. So in this case, we have our vertical components as Fn, Fay, and Fg. And so I'm actually going to set up my balanced force equation that way. So I have Fn. Now we also have to account for the direction. Fg points downwards, and so does Fay. So let's go ahead and use those numbers. So we're going to end up having Fn is my unknown. Once again, let's go ahead and get Fg up here. And that's going to be 1,000 newtons. I know a lot of you just love to write that down right away, which I love. It's great. But for me, I'm just going to be a little bit more careful in my work so that we're all clear on where it comes from. So G is 10 meters per second squared, and this is mass M. And so that's what I'm using in my formula right here. All right, so I have Fn minus 1,000 minus my Fay, which is 138 newtons. And so that's going to give me a normal force of 1,138 newtons. Now, whenever we ask for the maximum static friction force, we're going to basically say, and also I need to change one thing here, this should be the answer to C that we use. So for part C, and this should be part D, all right, good. So use the answer to B to calculate the maximum possible static friction force. So that is going to be us using the coefficient of static friction and the normal force according to the formula. And the maximum static friction is the static friction coefficient is 0.2. we're going to multiply that by the normal force, and that's going to give us a friction force of 228 newtons. All right, so that's the maximum static friction. So now to see if it moves, horizontally, we have to look at FAX and compare it to the maximum static friction. And when we compare this 164 Newton force versus the 228 newtons, the answer is no, it does not move, because 164 is less than 228 newtons. All right, so that's part D. Moving on to part E, it says, now we push with 500 newtons at 35 degrees, and we want to ask if the lawnmower moves. And if so, we want to calculate its acceleration. So to be clear, for this part here, and I should actually call this part E, I don't know why I did that. I want to be absolutely clear that for this one, we have to actually start the problem over again. And let me be clear on what I mean. So, the free body diagram stays the same, and I have no problem using that right here, just to be safe. Well, there we go. So I'm fine with the free body diagram. But now what I want to do is I want to get a little clearer on what the forces are. So let's go ahead and get FAX and FAY. So FAX is going to be 500 times the cosine of 35, and FAY is going to be 500 times the sine of 35. And when I work those out, this is going to be about 410 newtons when I round. And here, 500 times the sine of 35 is going to give me 288 newtons. All right. So continuing with this idea here, we want to now calculate the normal force. And once again, I'm going to use the same equation as I did before, balancing vertical components. I'm going to say that Fn minus Fg minus the applied force's y component or vertical component, they all balance. So Fn in this case is going to be, I'm going to take the 1,000 newtons, and I'm going to subtract off 288 newtons from the FAY. And so I'm actually getting a normal force equal to 1,288 newtons. Okay? Now, that's the normal force. You know what? I should be a little bit more careful about that. So this is going to equal 0. And then I'm going to isolate and get that Fn is 1,288. So, now let's go ahead and get the maximum static friction force. When we calculate that, it's going to be 0.2, which is mu static, times the normal force. So that's going to give us 0.2 times 1,288. So and that's giving me a friction force of 258 newtons as my maximum possible static friction. So let's compare. FAX is 410, which is greater than the maximum static friction. So yes, we move. So the answer to the lawnmower moving now is yes. Now we calculate its acceleration. And to do that, since we know it's accelerating, we know it's moving, we're going to switch over to kinetic friction. So we're going to have FAX minus the force of kinetic friction is going to equal m times a. Continuing, we're going to have 410 newtons as FAX minus, now we need to get the kinetic friction right here. That's the kinetic friction force is going to equal mu kinetic times the normal force. And mu kinetic in this problem, I believe it's 0.1. Let me confirm that. Yes, it is 0.1. So that's going to be 0.1 times 1,288. So we're getting a friction force of about 129 newtons. Which I'm going to use right here. So 410 minus 129 equals 100 times A. So I'm getting 281 equals 100 times A. And so when I actually isolate the acceleration, that's going to be 2.81 meters per second squared. Let me just double check. Now, here I did have a small little thing I should have done. I should have given you a value for its velocity. So here's what we're going to do. It says draw a free body diagram. And what we're going to instead calculate, we're not going to calculate every little thing here. But what we're going to calculate instead is we're just going to calculate the acceleration. There we go. So to that end, first let's change the problem. Once again, we let go of the lawnmower, so that means we no longer have that pushing force. So we've got a normal force, we've got the gravity force, and we have the force of friction. This is very much like a problem we've done earlier, so I'm going to do it a little bit quicker. So first I'm going to get the normal force. That's Fn minus Fg equals 0. And when we solve for Fn, since we know that Fg is 1,000 because that's m times g, we're getting 1,000 newtons right here. Now let's get the friction force. The kinetic friction force is going to be 0.1 times Fn, because that's mu k. And so when we solve, we're going to get that our kinetic friction force is a mere 100 newtons. Now let's get the acceleration. So horizontally speaking, we don't have any applied force here, so it's 0 minus F of friction equals m times a. So that's negative 100 equals 100 times a. And so that means our a is going to be equal to 1 meters per second squared. All right, so that is it for this particular problem, and we'll finish up with the angle problem on the next page.